Hello everybody and welcome. Today will be your first remote lesson for mathematics about chapter 7 in your book, which is about two-dimensional shapes. We're going to learn a lot in this chapter, but the common theme is that we will be learning about properties of two-dimensional shapes and that we're going to use these properties to become better at calculating angles. For example, at the end of the chapter, you'll be able to solve questions like this. We are not going to get into this question now, of course, but as you see, it assumes that you know what a parallelogram is, and it also assumes that you are aware that what that implies for the angles. For instance, that opposite angles in a shape like this are always equal. So knowing these things will provide us with a lot of tools to solve ever more complicated mathematical puzzles, which is what we all enjoy doing so much, of course. But in this class, we will not be doing anything new yet. Instead, I'll remind you of some previous concepts and techniques on which you will do some exercises in the prior knowledge of your book. So we will revise some basic terminology and techniques involving angles. I'll give you a quick reminder of how to draw triangles based on given instructions. And I will remind you of what we mean by line symmetry and by rotational symmetry, and of how we can draw the mirror images of shapes when reflected in lines or in points. Because these are things that you have already done before, I'll try to do this at a brisk pace, so feel free, of course, to pause the video and repeat something if I went too fast. First, let's talk about angles. An angle, as you know, is basically what happens between two rays that meet at a point. That point we call the vertex. And the angle is literally the space between those rays. And we can measure the size of an angle, and we usually do that in degrees. If the angle is small, then so less than 90 degrees, then we call it acute. And if it is precisely 90 degrees, we call it a right angle. It can become bigger. If it is between 90 and 180 degrees, we call it obtuse. And if it is precisely 180 degrees, which it will be soon, we call it a straight angle. Now, as you see, I can go on rotating this arm of the angle beyond 180 degrees, and then we get an even larger angle on this side. But now I also have a smaller angle on the other side, and usually we take the measure of the smallest angle. So this would now have become an acute angle again. And we can also see, of course, how many degrees I will have turned when I have made a full circle here, because that will be 360 degrees. So a full angle or a full circle has 360 degrees. Now, knowing how many degrees right and straight angles are helps us perform certain calculations. For example, in this shape, I'm given the information that one part of angle A is 30 degrees and that the whole of angle A is a right angle. So when asked to calculate angle A2, I can use this information. I can say, I know that angle 2 will be 90 degrees minus these 30 degrees. Now, where did I get the 90 degrees from? That's from the fact that this is a right angle. And now, of course, I can simplify or calculate this difference, and I get 60 degrees as my answer. Similarly, when my angle is part of a straight angle, I know that the total number of degrees has to add up to 180. So here I would write something like angle S2 together is 180 degrees because it is a straight angle. And then S2 will be that whole angle minus this part that I want to ignore. So 180 minus 50 degrees, which simplifies to 130 degrees. Now, if I want to calculate S3 here, I can do the same trick again. I can do 180 minus S2 is 180 minus 130 is 50 degrees. So I get 50 degrees. And this is not a coincidence. As you know, this always happens with what we call vertically opposite or simply opposite angles, which you get when two lines meet at one point. Those angles are always equal. So this gives us three basic rules for calculating angles. A right angle is 90 degrees, a straight angle is 180 degrees, and opposite angles are equal. And this is basically what the first exercise in the prior knowledge will be about. The second one will be about drawing triangles based on instructions. Now sometimes you'll get relevant sides and angles, but sometimes you may only get the sides of the triangle. And in those cases, you'll not need to measure out an angle, but you'll need your compass. And I will quickly remind you why that is and how that works. Let's say we want a triangle with AB 5 centimeters, side AB 5 centimeter, AC 4 centimeter, and BC 6 centimeters. Now we can simply start by drawing the first side, and I would usually pick a horizontal grid line for that. Now the question is, of course, where vertex C needs to be. And the trick here, which is quite elegant, is that we can translate the information here to shapes on our paper. AC equals 4 centimeters. Well, that means that C has to be somewhere at a distance of 4 centimeters to point A. And that means that it has to be somewhere on a circle around A with radius 4. Let's draw that circle. These are all the points where C could be, all the points where AC would be 4 centimeters. So that's still a lot of possibilities. Could be anywhere here. But this is not the only information we have about point C. We also know that BC is 6 centimeters, and that means, for the same reasons, that C has to be at a distance 6 from point B, so it has to be on a circle with a radius 6 around point B. Now these circles intersect, they meet in 2 points. And where they intersect, we find points that are both at a distance of 4 from A and at a distance of 6 from B. And that is what we need. So we pick either of those points, we plot the vertex C there, and now we can finish the triangle. Moving on to the final topic, symmetry. Symmetry means that a shape stays the same after we've done something to it. And the simplest form is probably line symmetry. A shape has a line of symmetry, is line symmetrical, if we can fold that shape along a line so that the two halves overlap. Or, and this means the same, if we could mirror it in that line. So for instance, this shape is line symmetrical because we can look at this line as a line of symmetry, and then we can fold the left half onto the right half and they overlap precisely. Or if I would place a mirror here, then the right half would be the reflection of the left half, or the other way around. So, by the same definition, is the diagonal of this rectangle a line of symmetry? Well, no. If I fold it along this line, then I get two parts that cannot be made to overlap. So this diagonal is not a line of symmetry. Of course, the rectangle has other lines of symmetry here and here, to be precise. So it is line symmetrical, but this is not a line of symmetry. Another major type of symmetry is what we call rotational symmetry, which means that a figure is the same as its original after we have rotated it around a point under a specific angle. For example, taking this traffic sign, I can put a point at the center. So I have made a copy here and put a point at the center. And if I rotate the shape around that point by the right number of degrees, in this case 120 degrees, the shape looks the same again. So that means that this shape is rotational symmetry. Now, both for lines and points, we have to be able to draw our own symmetrical shapes by reflecting a figure in a line or in a point. And the last thing I'll show you today is how this works. Let's say we want to reflect triangle ABC here in line S. Then the technique is that we first reflect every vertex in line S and then connect the vertices, draw the mirror image of the entire triangle. So starting at vertex A, we place the perpendicular line of our protracted triangle on line S, so like this. And then we slide the triangle so that the ruler meets point A, vertex A. Now we draw the perpendicular line to line S that goes through A, like this, as long as we can copy this distance. So this is 5 centimeters here, and this is 5 centimeters here. And then on the other side, we put the image of vertex A, which we call vertex A prime, an A with a small apostrophe right next to it. We do the same for the other vertices. So we mirror this. This is perpendicular to line S, and these two distances are the same. And this is perpendicular to line S, and these distances are the same. And of course, I show that in my drawing, and I show that these are perpendicular lines. And then once I have drawn all the images of the vertices, A prime, B prime, and C prime, I can draw the image of the entire triangle, leaving, of course, all the constructions that I used here to find the new vertices. Something very similar happens when we want to when we want to reflect a shape in a point. So let's say we want to reflect triangle ABC here in point P. Again, we reflect the vertices first and then we connect them. And now the trick is that we simply have to extend the line from the vertex to the point of symmetry. So we draw a line segment from A to P. We measure that line segment and we extend it by the same length. So this is about 6.7 centimeters, and this is also 6.7 centimeters, and these are on one line. So point A prime will be over here. We do the same for the other vertices, so from B to B prime, and from C to C prime, and once I have all the vertices of the image of the triangle, I can connect those vertices and draw the entire triangle. I think this should be all that you need in order to be able to complete the exercises in the prior knowledge. So good luck, and feel free, of course, to ask questions if you need to. See you next time.